Okay, good afternoon, everyone, and perhaps good morning or good evening there. So, welcome back to IPC. Today we have Dr. Yoshinta Setyawati. Uh, she's currently postdoc at the Netherlands, and today she will share her research topics about gravitational wave. Okay, Dr. Yoshinta, you are here?
Yeah. Hi, can you hear me?
Yes, we can hear you.
Cool. So I will share my screen. One moment.
Yes, we can see your screen now.
Okay. Okay, one moment. Okay, shall we start or we still wait for other participants?
I think we can start already. Okay, thank you very much, Dr. Yoshinta. The time is yours.
Thanks. Okay. Yeah, hi everyone. So this is the last presentation, I think, of this IVC summer course in 2022. It's a pleasure for me. And I would like to say thanks to the organizer for inviting me here, and so that I have an opportunity to give an overview about gravitational wave science and modeling. And my name is Yoshinta. I'm a postdoc at Utrecht University, as well as Univ in Amsterdam. And since this is the last talk, I would like to give some. I would like to give some interactive, playing some interactive activities, so I hope people are not that sleepy, especially after lunch. But here for me too, and because this is very early for me. And I would like to have the questions at the very end of my presentation, unless if you have some urgent questions, like you can't hear my voice anymore, or I don't know, some urgent questions, just write it in the chat. I can't see the chat because I'm presenting, so I hope one of the organizers would be kindly enough to help me to see the chat if there is something urgent there, and then it just interrupt me there. Okay. Yeah, let me start with the introduction. So the Utrecht is located in the Netherlands, and here's you can see the red area. Here is Utrecht, is in the center of Netherlands, and normally if you take a train from far away from this part or from any other part of the Utrecht, you get a connection in from the Netherlands, any parts of there, you get a connection in Utrecht. So it's very central, it's nice for connecting, and it's a very nice city. So sorry, can I ask help from Buluki maybe to set me not as a co-host, because I always get the notification. Yeah, thanks. So okay, so that's about the Utrecht, and I show you here the university, and here's on the top right you can see the photo of the university and its friendly professors. They ride the bicycles around to promote to the primary school and to promote science and university in primary school. So it's a bit too early, yeah. As you can see, the topic of my presentation and my research is about gravitational wave. And you may first think that I work in this long observation of its gravitational waves, just like in this photo. But I should say, no, we don't have that in Utrecht. It's very dense, and it's just not possible to build an observatory like that in Utrecht. Yeah. So what I work on is in the theory, and I mostly work behind the monitor, behind the computer, and sitting the whole day analyzing the signal. Our group itself was just been founded around 2 years ago, so it's relatively new. Gravitational Wave Group in Utrecht University. We have several PhD students, masters, postdocs, bachelor. And here's the photo of the building where I work at. So the focus is about gravitational wave modeling and testing general relativity. Okay, so that's a brief introduction about myself. And since this is an international, oops, sorry, I can't move my slide. Okay, since this is an international conference, yeah, I would like to know about you. I would like to know more from which country are you from. So to do this, you can go to www.menti.com. I hope you can reach a browser or via your phone or maybe your laptop, and then enter the code 44124933. I give you some time. Go to www.menti.com and use the code 44124933. Right, so you write where you're from, and then I can see here. Okay, 4 people. Okay, how many participants do we have now? 47. Cool. So I'm still waiting. Okay, I don't see any more. Okay, 18. Okay, we have around 21 people. It's interesting. I think most of you are from Indonesia. Then I see Malaysia, India. I see Kazakhstan some time ago. Yeah, Kazakhstan. Yeah. So yeah, it's very interesting that you come from a different area, from different countries, and come here together to join this this is very diverse, very international. Okay, so I should continue with the material. That's very interesting. You can also play around later. Yeah. So I will continue with the material. This is the contents of my talk. I'll give you a brief introduction, and then I'll go to the modeling gravitational wave, analytical, numerical relativity, and my focus in my research focus is in the semi-analytical in spiral merger ring down, where I will discuss about 2 different model. Here is the phenomenological and the reduced order modeling. And I'll give you a bit overview about the future of gravitational wave science, and I will close it with summary. So, okay, the introduction of gravitational wave, a brief history about that. We start with 1916, Einstein's general relativity. Sometime later, Einstein predicted the existence of gravitational wave as a consequence of general relativity, where gravitational wave is seen as a small perturbation in spacetime, for example, by the motion of compact objects such as binary black hole, binary neutron star, or neutron star black hole binary. So the characteristic of a gravitational wave, you can see in this plot below here, it has two polarization, plus and cross, and it stretches in one dimension and squeezes on the other simultaneously. There is a funny story about Einstein and gravitational wave itself. So around 1936, Einstein was about to submit a paper, and he was convinced that gravitational waves do not exist at the time. So he changed his mind a couple of times, yeah, and then he talked with his colleague some time later, and then he noticed that there was a little mistake in his calculation, and then he thinks that gravitational wave exists. And several months, or I don't know, maybe years later, he changed again, and then finally he concluded that gravitational wave maybe exists. So the detection of gravitational wave itself is very challenging. That Einstein himself, he doubted at some point, he doubted about the existence of this wave. Okay, let me continue. Several years later, many decades later, in 1974, there are two guys, Hulse and Taylor, and they observed the orbital shrink of a neutron star. So pulsar is a spinning neutron star, and they observe the orbits over time, and they noticed that it shrinks due to gravitational wave radiation, and it was known as the first indirect detection of gravitational wave. These two guys got the Nobel Prize from this observation. But the hand of the gravitational wave is not the end yet, so we still continue after that. And 4 years later, it's the start of the construction of the LIGO interferometer to do the direct detection of gravitational wave. So it took a long time, yeah, from the 1978 to 2000s, where this LIGO founding fathers try to work on it. Like maybe they work on the grants, they develop the technology of the interferometers. They also improve the model, the gravitational wave model, and around 2000-ish, the initial LIGO started to observe, and it was also a breakthrough in theoretical part where numerical relativity finally works to model gravitational wave in 2005 by Pretorius. He was a PhD student at the time. So it was really an interesting decades in 2000s in the development of gravitational wave. And then several years later, the LIGO interferometers was upgraded to the advanced LIGO, so it has a better sensitivity. And then in 2005, we observed the first detection of gravitational wave from binary black hole coalescence. Since then, there are more and more detections, and gravitational wave networks are not only from LIGO, but we have Virgo, Kagra, Geo 600, and more. We prepare for the next generation of detectors. So similar to other wave, gravitational wave also have some spectrum. So different frequency band has different sources and different detectors. The focus of my talk is in the compact binary in our galaxy and beyond. So especially about black hole, and it will be this is detected by the ground-based observatory. This is a photo of LIGO, for example, and the frequency range is between 20 hertz to kilohertz range. Yeah, so this is the focus of my talk. And before we go further, let me give you a brief introduction about how the interferometer works. I took this from YouTube, and LIGO has an L-shaped interferometer, so it's 90 degrees. The way it works is that a laser is beamed to the middle of the interferometers. It has the same length. Each arm has the same length. In this case, for LIGO is 4 kilometers. Then it bounces back and forth so many times in the mirror at the end of this arm, and then the signal is collected back at the detector. And if there is no gravitational wave signal, then they will cancel each other. But if there is a gravitational wave signal passing by, then one arm is longer than the other, and therefore we will see signal in the detector. Okay. So as I said before, since the first detection, we have more and more observatories. So now not only the 2 LIGO detectors in the USA, Hanford and Livingston, but also Virgo in Italy, Geo 600 in Germany. So the arm length is only 600 meters for each arm. Kagra has just joined our our observation around 2 years ago. Is a 3 kilometer underground observatory in Japan, and LIGO India will join us maybe around 2 or 3 years later. It will be put in India. So there is an interesting story about this. The collaboration actually proposed to build LIGO in India a long time ago. I think around, I don't know, above 2010, before the first detection. And it's been sitting for a while. The proposal has been sitting for a while in the Indian government, waiting to be approved. And then once we have the first detection, several months later, or I think in 2016, LIGO India was approved to be put there. So now it's in the construction time for LIGO India. And it's very interesting. It will have, I think, 4 kilometer arm length, just like other LIGO. Okay, I talk about the first detection. So I will also talk more about that, the hype of the GW150914. It was the first detection of gravitational wave from LIGO. It comes from the collision of 2 black holes, or what we call binary black hole. So the convention of the naming is that if you see this GW150914, 15, the first 2 digit is the year, and then the month, followed by the month, and then followed by the date. Here you can see the signal from 2 observatories in Hanford and in Livingston, USA, and the reconstructed signal, and the numerical relativity is this red and blue one. This is our model. So at the time of the detection, the signal agreed with the model of 2 binary of a binary black hole coalescence. It's interesting that the first detection yielded so many prizes, from the Breakthrough Prize, the Princess Asturia Prize from Spain, and even Nobel Prize, the Nobel Prize in 2017. So we may ask now, why is GW150914 important as the first detection as from LIGO? It's a proof of the existence of the missing Einstein's waves, the gravitational waves. It's an excellent test of general relativity. It also proved the existence of black hole, binary black hole coalescence. And we use this as to observe our universe through gravitational wave. For example, we can learn more about the evolution of the binary. We can also use gravitational wave as a standard siren in cosmology to constrain the Hubble constant. And also to learn the existence of violent events in the universe and exotic objects, or also to test alternative theories of gravity. So maybe not only general relativity, but also maybe some kind of other theories. Okay, since then, there are more and more detections we observe. So here I show you in the plot, the blue circles are the detection of black holes from the ground-based interferometers, LIGO and Virgo, and so on. And the orange is the detection from LIGO, Virgo for neutron stars. We have seen so far binary neutron star and neutron star black hole binary during the 3 observing runs. And the red one is the black holes from electromagnetic, so from X-ray observation. And the yellow one here is the neutron star observed from electromagnetic. So we have more than 50 binary black holes in the last in the 3 observing run that was ended around 2 years ago. So I mentioned about observing run, and maybe you're confused. What is it? So the way it works is that the interferometers have commissioning time and observing run. Observing run. So commissioning time is when the experimental people try to upgrade the detectors such that it gives a better or higher sensitivity. So in the commissioning time, it is normally work for like a year or 2, something like that. And there is no observation at the time, so they work to improve the detectors. And then when it ends, the observing time start again. And so that's the time when we observe, we get the data from the detectors. And then after that, they do the commissioning again. So it's alternate. At the moment, we have so far 3 observing runs. And now the detectors are put into the commissioning time, and we observe again, hopefully in March next year. So if you're curious what we see from the data, what we get here is here's the dark blue is the data we get from the interferometers, and we may just think that just look like noise, just noise, noise, and noise. Okay, but if there is a gravitational wave signal there, it is like this light blue curve. So it is buried inside the noise. Yeah. And the way we analyze it is that we filter it through many waveform templates. So we have a model, and then we created many waveforms with different parameters. We filter it until with Bayesian inference until we find this. If there is a signal, if that agrees well with we have some threshold, then we say that this is a detection. So here I show you how in the parameter here this is the parameter of the templates, M1 and M2. I use the convention that M1 is greater than M2. Yeah. And each point here has a different parameters of the model. And you can see here the green is just denotes that this is some interesting area. I don't know, from objects that maybe we don't know, and the orange is from the area of the neutron star, binary neutron star collision, and the blue area is for the black hole collision. So it's very dense, so you can't see the point because it's very small, but you can see here from the density. Okay, so again, once we have this curve, the light blue curve, how do we translate it into the physical evolution of the binary? So again, I come back to the first detection plot, and here's the signal. If you see in the previous plot, you see how the model looks like. It's smoother, yeah, just like this is smoother. And when they're relatively constant, like around this area, then this is when the binary is orbiting each other. It's what we call the in spiral phase. And then they move faster and faster close to each other, and they collide. They collide here, or they merge. Normally in the data, we define it when the amplitude is at the peak amplitude is when they collide. And then the ring down, so they become one big black hole, and here's the ring down. Okay, so I talk about a bit about binary black hole parameters. I would like to categorize it into two big categorization: intrinsic and extrinsic parameters. The intrinsic parameter is the parameters of the binary itself. So that's the black hole parameter itself that we consider in the gravitational wave. While the extrinsic parameter is the parameter relative from the location of the black hole to the location of the observer, so to us or to the interferometers. So here's, for example, the intrinsic parameters. We have two masses, mass 1 and mass 2. The spin components, spin is the rotation of the black hole itself. So we have chi1 and chi2 for the two bodies, yeah. And each of them has three components, x, y, and z. So we have 6 spin components. The eccentricity is the elliptical orbit of the black hole. And for the extrinsic parameters, we have distance, the luminosity distance. The inclination angle is the angle between the observer to the total orbital angular momentum, as you can see here. The sky location, you can see it as the right ascension and declination. Polarizations, angle, time of coalescence, and phase of coalescence. So if you want to play around with different parameters, you can go to this visualization. This is the visualization I made on GitHub. I focus on the intrinsic parameter because normally in waveform modeling for these extrinsic parameters, we can scale it with, let's say, with the strength of the signal. So we can scale it easily for the extrinsic, but for the intrinsic, we have to model it carefully. So that's why I focus this on the intrinsic parameter. Yeah, maybe I ask help from the organizers to write it in the chat, maybe, so the participants can click it easily. I will also upload my slides later in the Google Drive. Okay, so if you click this, you will go to the node, and then there is a logo, the binder logo, and you click that, and it will take quite some time, quite a long time to build that, because there are some dependencies, but you don't need to do anything. You don't need to install anything. It will do the things automatically, and then you can play around with that. Yeah, so another thing I wanted to say is that for the spin components, yeah, we have 6 spin components, but the way we work is that we start from the simple thing first, and then we expand further and further when we model something. So in that case, first there is an interesting a unique system of the black hole, where if the spin is aligned to the orbital plane, then we only consider the z direction. That means we only consider the two spin components, the z direction, chi1z and chi2z. So we reduce complexity on that. Instead of 6 dimensions, we have 2 dimensions. And then we expand it further, we make a more complex model, and so on. So that is interesting. And now I have a quiz, and I hope you can follow the quiz. You can go again to the www.menti.com with the same code as before, 44124933. Or if you have opened the browser before, you can go there and you can maybe refresh, or maybe you don't need to refresh, and you can fill in your name. I think it's IVC minus something. You can fill in your name, and I will wait you to join. Now I see 23 people. I will wait until you join. So when you write your name and then you submit it, and then I will continue with the question. Okay, 36. Oh, we have 50. Are there more or 38? Okay, I will okay, I'll continue with the question. I think it's not no more people join us. Okay, 38. Okay, I will continue with the question. Be ready. Oh, enter. Oh, answer fast to get more points. These are not binary black hole parameters in gravitational wave analysis. Just with which options apply. You can only choose one. And 20 seconds from now. Fast, fast, fast. Three, two, one. Okay, 5 people don't answer. Okay, so okay, 12 people answered correctly. Tidal parameter and electric charge. These are not the parameters of the black hole in gravitational wave analysis. Thanks for these 12 people who pay attention to my talk to the previous slide. Okay, that's interesting that there are more mistakes than the right answers. Okay, for these 12 people, keep up the good work. Thanks. And here is the leaderboard. So this is the point you collect. IVC9. Who is IVC9? Okay, there is no name. Woohoo! Okay, let me continue to modeling gravitational wave. Yeah. Okay, for the modeling gravitational wave, I give you a bit of overview here. This is the frequency and mass ratio. So that depends on different frequency and different mass ratio. I should say that I don't talk about this system. This is the extreme mass ratio in spiral system. It's when the black hole orbits a supermassive black hole, for example. So this mass ratio is very high. For example, if a small black hole orbiting the black hole in the center of our galaxy. I don't talk about it. And since I took this plot from Harald Pfeiffer's plot, and he used different convention, so this is the mass ratio is less than 1. This is basically what I talk is here. I always say M1 is greater than M2, but this is M2 divided by M1, so it's always smaller than 1 here. And what I wanted to talk is in this area, yeah, when the binary is orbiting each other, it's the in spiral the spiral phase, and this is modeled well by the post-Newtonian theory. When they move faster um, to merger, we can use here numerical relativity, and then they go to ring down. When they merge to each other, they go to ring down. But in the next couple of slides, I will focus on these two, post-Newtonian and numerical relativity. Let me start with the analytical approach to model gravitational wave. And I hope you don't stress out with this so many formula. You can ignore them. I will explain it later. So the analytical approach is what I present here is the post-Newtonian approximation. So the idea is that if the two black hole orbiting each other, yeah, then their orbit shrinks due to gravitational wave radiation, to the emission of gravitational wave radiation, and then because their orbit shrinks, so they move faster and faster. So the energy over time, which we call this flux, then it has some relation with the speed, so the phi. So this post-Newtonian is the expansion of phi over c. There is a different formulation of these, which I don't put it in my presentation, but these two depends on the speed of the phi here. So okay, the idea is the expansion of that, and then it's modeled well, the spiral of the binary. And here I provide you with the strain of gravitational wave in the frequency domain. Just like any other wave, it has amplitude and frequency. The amplitude is A here, yeah. And then this is some frequency, amplitude and phase. This is the frequency, and everything inside this bracket is the phase of the gravitational wave. So the amplitude itself depends on some parameters here, which I write what's the definition of the chip mass. And see here it depends on on the location of the source and the observer or the interferometer. So this has something to do with the location. And then I go to the phase, this phase. It also depends on several parameters here. And if you see, this is the sum of k, sum of psi k, where psi k itself is defined here, and it depends on different terms of this alpha k. Yeah, this is the sum of this. So this is what we call with the post-Newtonian order is the number of the alpha k divided by 2. So k divided by 2. So in this case, this is the last number is 7. So this is the 3. That means this is a 3.5 post-Newtonian order. It's what we know in the, it's in the convention. Yeah. If you're interested into more detail in this theoretical, I suggest that you read a nice textbook by Mayori in 2008 and Living Review in Relativity, so you can access it freely from the browser from Luc Blanchet here in 2014. This formula is 3.5 post-Newtonian I took from Arun in 2006. And the idea is that if you have more and more order, you have higher order, let's say you have alpha 8, then you model it better than if you have less order, let's say alpha 7. So alpha 8 is 4 post-Newtonian order, so you can model better. So far I talked about the frequency, but for the amplitude itself, this is from the paper in 2006, but the amplitude itself is also expanded just like the phase here. But I don't have space anymore to write, and I don't want to stress you out with many formula. So this is also work like the phase where you see more and more order of the amplitude. It looks complicated, but actually it is easy because if you write this one by one in your Python code or C code, MATLAB, Mathematica, whatever, you can with a waveform model. So you can generate a waveform model from here, and it's straightforward and it's fast. Yeah, this is interesting, a nice approximation. However, when the binary moves fast to each other, yeah, when they move faster and faster, the post-Newtonian approximation breaks down. So that means even though you have alpha 8 or I don't know, maybe alpha 9, it's still not good enough when it's close to merger, and then the model is not good enough for that area. Let in spiral merger and bring down. So the solution comes from numerical relativity, and I should point you to some to the lecture in day 2. I think it's the basic of numerical relativity by Dr. Hakim. The idea is to solve the Einstein's equation numerically, and that means you solve this through a supercomputer to you you model this with different, I don't know, with different parameters, and it takes a long time, but also you have I think it's better if you have access to parallel computing for this. The method of the numerical relativity is that we split the space-time into space and time, or 3 plus 1, and then the dynamic evolution of a binary black hole according to the 4-dimensional Einstein's equation is reformulated as an initial value problem. The technicalities, for the numerical relativity, you would make a grid, yeah, a grid, and then there you put the location of the black hole, but you can't okay, you put the location of the black hole, and it has the topography of a wormhole here, and then you start to evolve that, and it will change the topography like this trumpet topography. So this numerical relativity um, simulations run for a long time. So it's maybe it takes months or even a year. So for one simulation, so it's very computationally expensive, and you can only get the waveform short. So it's sometime before the merger. If you make it longer, then I don't know, it takes ages, maybe 1 decade or so. I don't know. It's very long. Um, so it also needs human resources, because someone who runs this simulation has to computer sit. So like it's like babysit the simulation, but for computers. So they have to check from time to time if the simulations is working fine, if there is no problem. Maybe the problem is with his code, or maybe with the computer he used itself. So it needs a lot of attention. Yeah. So before I go further, I would like to summarize what I have talked before between the two models, the analytical and numerical relativity. So analytical is less accurate to model, especially when the binary when the binary moves faster towards the merger, while numerical relativity has a better accuracy in that area. However, analytical waveform like post-Newtonian is very fast and very straightforward, while numerical relativity is computationally expensive. Therefore, only a few simulations are available. Although over the years, the community builds more and more numerical relativity, but still the number is way fewer than the analytical waveforms. As here with analytical, you can build densely, you can build as many waveforms as you want in the parameter range. Okay, so what do we need? We need a model that has the only the benefit or the strengthness of these two. So you can see from the red ticks here, we need a model that's accurate, have a good accuracy, but also we can generate it fast, and we can generate as many waveforms as we want. We can generate it dense. That's what we want, yeah. So the idea would be like to have full waveform where some part of it, the red area, the red curve here is the post-Newtonian, and the blue curve here is the numerical waveform. And then we stitch them together like this black dot here. We stitch them together and we make it as a full waveform. This is what we call with hybridization. You may have heard it from biology, hybridization. But before I talk further about that, here's I will talk. There are several models that try to do this, good accuracy but also fast. The effective one-body model, phenomenological family, the reduced order modeling, and NR surrogate. In this presentation, I will focus on these two, phenomenological and the reduced order modeling, or we call this ROM, the ROM model. So let me start with the phenomenological model. Since I talk about hybridization, you may think it as in biology here. If you want to hybridize a horse and a zebra, then let's say here, this is the horse and this is the zebra, and you want to join them, okay? Then maybe you work on this white area. So similar to that, in the phenomenological family, they start from the ischias system first, so the aligned binary, which means you only have 2 spin components. So it's easier than 6 spin components, of course. And then they have this parameter range. This is mass ratio from 1 to 18, and this is different spin. And they put some dots there. So in this case, for the phenom D has this red dot. So this is the location of the. So if you see how you read it here is that this dot has a mass ratio 18 and spin between 0.5 to 0.25 to 0.5. And so they have numerical simulations there for each of the red points here. And they made a waveform and calibrate to these red points. So they have, as I said before, the way to do that is they have these numerical waveforms, and then they split it into the amplitude and phase of the waveforms. So here's the plot of the amplitude, and this is the plot of the phase, the bottom one. And from there, they split into each amplitude and phase. They split it into 3: the in spiral, intermediate, and merging down. So this is the first region in spiral. They work mostly on the intermediate, and this is the measuring down. The goal is that to ensure a smooth transition from the in spiral to the measuring down. So this is what they work most at. The same for the phase. So if you see here, again to the analog of this biology, they work on this white area, but I should say this can't at all. The authors, they work better than the biologists who created whatever creature it is, because this model is has a good accuracy. When they compute, the agreement is good against the calibration, the calibrated waveforms, numerical waveforms, and this model has been used in the analysis of the first detection and the first observing, the 2 observing runs. Now we developed this model more and more, but still this is a nice basic of this phenomenological family model. So the way they do the smoothing here is that they do some fitting procedure with the polynomial interpolation, or with different kind of smoothing and fitting procedures. Maybe you have heard before the basic of modeling in the first week about fitting procedures. Okay, so then let me go to the second one, is the reduced order modeling. So the phenom model is we can generate this phenom model very fast, but it's not enough. We also want to make it faster, to make a faster model. So this comes from the reduced order model, or ROM. The idea is that back to linear algebra, if you maybe have heard in, or if you remember, maybe some years back, if you have linear algebra about the matrix, that if you have an orthogonal matrix, you can decompose it into two orthonormal matrices and one diagonal matrix. But before I go there, let's imagine if you have a set of waveforms, so many waveforms with different parameter, you can arrange it into a matrix form. Yeah. So this is a visualization where the different rows here means that you have different waveforms with different parameters. So let's say maybe this is mass 1, 5, and this is mass 1, 2, and so on. Okay. And then the columns here, this is the point in time. So, or the point in time or the point in frequency. So it runs time and in time or in frequency. In this case, for the visualization, I use the time. So you arrange this in a matrix form, where in reality, what you see is just numbers. This is just numbers, but this is just for visualization. In reality, it's just numbers, and from there you use singular value decomposition or SVD, and you can decompose it into these three matrices. Here also visualization of these two matrices. This is called left and right singular matrix, and the there is a matrix in the middle is called the singular values, and in the singular values there is only number in diagonal, so the rest are zero, and it's only the diagonal has number. So that's why I don't make a visualization, or this paper also doesn't make a visualization for this singular value, because it's just a diagonal matrix. Yeah. So if you have here, if you have L rows and N columns of P, you can decompose it into three matrices here. I repeat again. And the interesting thing is that this diagonal matrix, the number is sorted by the highest to the lowest, so it's descending. That means if you go further in rows, you get less and less numbers here. Maybe at the end you get like 0.1 or something like that. It's very small. So if you don't take full L rows, but let's say you take only 80%, which means you end here. Yeah, maybe you take maybe the numbers, if you sum the numbers of this diagonal compared to the total sum, then maybe you get like, I don't know, 80% or 90%. You don't get 100%, but the comparison is maybe you only get around, I don't know, 90% or something. Is it good enough? It's it depends on what you want to do. Yeah, if you want to have speed up, then you can use you can analyze this with fewer data. Okay, it's less accuracy. Maybe you only get 90% or something, but you can have the data fast enough, because you don't take all the metrics, all the rows here. So here is another visualization of the singular value decomposition. Again, if you have these L rows and N columns, this is the original U matrix. Yeah, it has more columns, and it has more rows and more columns for the singular matrix sigma, and it has more rows for the right singular value VT. But if you reduce it only to k number of columns, k number of rows here, you get less, but you can speed it up. So the idea is that in a poorer 2014, he wants to speed up the building of the effective one-body model and numerical relativity. So he started with one effective one-body model. So he had more than, I don't know, I think 1,000. He generated thousands of effective one-body model spread in the parameter space, and then here he packed it in a in a matrix form, just like I explained before. But instead of using all the data, he used only he decomposed it with a singular value decomposition, and he used only up to k rows or k columns here. But it has 99% contribution of the original data. And every time he wants to generate a new waveform, then he just take the projection of this model. So he just take some data and then interpolate it and then project it back. So the computational cost is in the interpolation. So every time he wants to make a new waveform, he take the data he saved, interpolate it, and return it back. And this is better than purely interpolation because the data is not smooth enough for interpolation. So it is better to decompose it and then interpolate it and return it back because it's smoother. And for technicalities, how he does that is that he split into amplitude and phase again, and then each of the amplitude, each of the component, amplitude and phase, is packed into this matrix form. And here you can see the mismatch is the 1 minus accuracy. That means the lower the mismatch, the better the results. And this is if you use more points. So if the k here is larger and larger, at the end is 100% here. If k equals n, then let's say 500 here, then he get a better and better accuracy. Of course, if you have less and less, then you have less and less accuracy. So another group adapts this method and apply it to numerical relativity because, as I said before, numerical relativity is computationally expensive and you only have only a few waveforms are available, and therefore they do this, and this is what we call with NR surrogate. So the idea is that they use like reduced order modeling, but for numerical relativity. So I will explain about the application of the reduced order model. In this case, this is for the update of the waveforms. So imagine if you have two models, one model has better accuracy, like numerical relativity, but it's very slow, while the other model has a better has a bad accuracy, yeah, worse than the numerical relativity. But it's fast to generate and you can generate it as much as you want. So let me call the slow model is the target model and the fast model is the basis model. So if you have these two different models, you can place it in the parameter space. In this case, symmetric mass ratio, or you can also say it as mass ratio. We can also convert it easily. And here is the spin. So you place the target model. For example, this is with a grid, so you can see it's regular. It has a regular grid, but you can also place it randomly. And you can generate more basis model as dense as you want in this parameter space. And again, you generate the waveform and then you split the amplitude and the phase. And here I show you again the visualization of the amplitude and the phase. Then you decompose it into with the SVD, yeah, each of the amplitude and the phase. You decompose it with singular value decomposition. Now you have three matrices for each component, amplitude and the phase. And then you save what we call with the projection coefficients. It's from the matrix multiplication. And then you interpolate it. Once you interpolate it, in your desired parameter. If you, for example, if you want to build a waveform with parameter in this white area here, you interpolate with the parameter of this white area. Let's say this is close to 0.25 and close to the spin is close to between 0.25 to 0.5. So it's your desired parameter. You interpolate it and then you use matrix multiplication to return it back. And then from there you have two components, amplitude and phase. And from this amplitude and phase, you build a new waveform by combining the two of them. So now you have the new waveform, which we call the enriched basis waveform, and it depends on the amplitude of the enriched basis and the phase of the enriched basis. So that was the idea. Again, the computational cost is mostly in the interpolation. So in this case, we have two-dimensional parameters, the symmetric mass ratio and the spin. But then again, if you go to precessing system, then you will have 6 spin components here and 1 symmetric mass ratio. So you have to do 7-dimensional interpolation. If you want to add eccentricity, maybe you will have 8 or 9 dimensional interpolation. So we have to think more if this is we have to think more with the more dimensional parameters for the future. Anyway, for this study, it was a proof of study, and here I show you the results of the agreement between the target and the basis. So the agreement is between 0.38 to 0.99. Of course, the good agreement is close enough to 1, then it's a good agreement. So it's between 0.38 and 0.99. But if we apply this procedure, then we improve it a lot. So now we have an agreement of 0.98 to 0.99. This is the agreement between the new model, which we call the enriched basis, against the target model. For example, in this case, we use phenom D, but for example, we can use numerical relativity on that. So it improves a lot. Okay, so I talk a lot about the modeling gravitational wave, and I give you a bit of overview about the future gravitational wave science, especially in the 2.5G and the planned 3G detector networks. It will be in 2035 beyond. So now we don't only deal with LIGO, Virgo, Kagra, and Geo 600. Geo 600 is a 600-meter. I have explained before. I hope it's in Germany. And not only that, there will be also other detectors such as NEMO. It will be built in Australia, and the focus is in the high frequency observations. So that means the focus mostly is the past merger. So that means in the ring dawn of the black holes or in the post-merger area of binary neutron star. So we want to know what happened next after the binary merger. So this focus more on that. And then there are some other projects. The Einstein telescope is a very interesting project in Europe. So it's an interferometer, but it will not be built as an L shape. So far, what I know is that it will be built as with a triangle shape, and then it has each arm of the triangle has the same length, and it's 10 kilometers long. So the site of the Einstein telescope is still in discussion. Maybe it will be put in Maastricht in Netherlands, or in Aachen in Germany, or maybe in Sardinia, is an island in Italy. So this is and to be honest, these 3 countries, they're still discussing. It's like they play tender, which of them to get the host the Einstein telescope, because it's very interesting project, and it's the future of gravitational wave science, especially in the ground best, because Einstein telescope will have a much higher sensitivity than the current detectors, observatories. The other thing is the Cosmic Explorer. It has an L-shaped classic interferometer, just like LIGO. So Cosmic Explorer will be built in America, in the USA. But each of the arms is 4 kilometers long. So it will also have a higher sensitivity than the current detection now. So I'm not even mentioned about the space-based detectors such as LISA, which also plan to be built around 2030-ish and beyond. So LISA will work in different frequency band. Anyway, in this 2035 plus, we will have a nice, I think we will have a nice network of detectors. We don't only have a higher sensitivity, but also stronger signal to noise ratio or SNR. And we expect to see more and more detections, but it will also come with a problem, because then if we see signal after signal, then they will overlap to each other. So the end of the signal may be overlap with the beginning of the next signal. And so we have to think about the strategy and how to model this signal for the future. We will need a higher accuracy, of course, because our detector will have a way better sensitivity. We also need a faster analysis. As for now, uh, we we do the parameter estimation and we already speed it up. The first one was like couple of months. We do the analysis, but now we do the analysis faster, like in the order of weeks maybe, and hopefully days, or even only within hours we can do the analysis. So the trend now is to have more faster and faster analysis, and we will need it for the future detectors. So in summary, we will have more challenges, and it's very exciting time in gravitational wave science. Okay, this is what is next. So what is next in waveform modeling? As I said before, we start with the simplest model. We started with a less parameter, and we expand more and more. So now the challenge is to incorporate more dimensional parameters. For example, like processing eccentric binaries, which maybe we will have to model, I don't know, 8 or 9 parameters, dimensional parameters. We need to develop higher accuracy and faster model to deal with high SNR in the next gravitational wave detector era or in the 3G era. The multi-banding models means that if we have more detector networks, so maybe one signal is first seen in LISA, like very early, and then it goes to the Einstein telescope, cosmic explorer, and then go to the ground-based interferometers like the LIGO, Virgo, Kagra, and so on, and then to the NEMO detector in Australia. So it will go from different frequency bands, and how we combine it so that we see the big picture of it. This is actually from one signal. This is from one source and not from different sources. This is also a challenge, and then improve waveform acceleration techniques. Again, it's the to speed up the parameter estimation and the analysis, and the extension to alternative theories of gravity. So now we work on modifying the gravitational wave model such that we can add some terms in the different theory of gravity. So maybe it's not only general relativity, we use it to test general theory of relativity. So I close this with summary of my talk. We have seen more gravitational wave signal, especially from binary black holes since 2015. The detection rate increases over the observing time as the interferometers are upgraded with better sensitivity. Therefore, we need faster analysis and to estimate the parameters of the signal. We noticed that one of the bottlenecks that makes the analysis slow is the waveform generation. And therefore, we work on that. We develop various models to tackle various parameters and to speed up the waveform model, but still providing good accuracy. The waveform hybridization in spiral merging down remain in the core of the analysis, with some applications, for example, in the reduced order modeling, to even speed up even more, and to automatically update the waveforms. Challenges for the future of gravitational wave detectors, for example, with different binary systems. As I said, I don't talk about the extreme mass ratio in spiral, where the small black hole orbiting a large black hole, like in the center of our galaxy. It is relatively more difficult um, uh, because we also have to expand to higher mass ratio there, and yeah, so we are currently are working on that, also with more dimensional parameters when we include let's say eccentricity and 6-dimensional spin parameters. So those are the challenges of gravitational waves. And then I would like to thank and allow you to have any questions, but I have a bit of more slides. I see we still have 15 minutes. Uh, this is just to point you to the references. I will share this slide in the Google Drive, so you can quickly see this if you're interested to gravitational wave theory. Such these are the two nice books by Mayori and Bernard Schultz. In short, I selected these references. They are beginner friendly, especially if you want to learn about gravitational waves. Yeah. There are some other references, but I think they're a bit more complicated than this. So if you are interested to the experimental side of gravitational wave, I suggest that you read these papers, and then the rest are about the modeling of gravitational waves. If you're interested more, unfortunately I don't give you a hands-on exercise for this, because I think you can learn independently, and there are very nice tutorials and very nice hands-on that you can find on the internet. It's from the LIGO, Virgo, Kagra scientists, where they make it this GWOSC. You can open this link here, and if you go there, you can see this. This is what you will see. Yeah, Gravitational Wave Open Science Center, and you go to learning resources, and then click on tutorials, and you can play around with the real data. You can even analyze the existing gravitational wave events, GW15 or 914, or some events afterwards. You can use a Jupyter notebook, so it's very easy for beginners. They also explain it step by step, what they're doing there, what's in these tutorials. So I really strongly suggest that you open this GWSC. There are some workshops on gravitational waves, and they are free of charge and online. So the thing is, you just have to apply for this. You have to register for that. You can click it here, and here you will see the calendar of the schedule of the workshop. So it's in different, I don't know, it's what, I think 2 times a year or something. So yeah, but this is free of charge if you're interested more, and they are also beginner friendly, because these workshops is the focus is for like students or people who just started to learn gravitational waves. If this is not enough for you and you're advanced enough with computing, I suggest that you install the softwares locally. The softwares that we use is the LIGO algorithm library, or LAL. Normally we use this for analysis, and it's a C-based code, but you can run it in Python as well. There's some of integration to Python. And you can see how to install it and the documentation here in this link, LAL suite. And if this is maybe not beginner friendly enough, then you can go to the next one. This is the PyCBC. I strongly suggest this, because this is very easy, to play around in. This is Python based software, and they have good documentation here. You can go to pycbc.org. You can generate a waveform. You can do waveform. You can also do waveform modeling, develop a waveform model there. You can analyze the signal. So this is I really strongly suggest this. If you're interested to numerical relativity, this is the Einstein Toolkit. This is an open software to do numerical simulations. They have a better and better documentation now, so you can just follow it step by step. I think it's better, but I think if you really want to run it to do numerical simulations, it will be better if you have access to a computer cluster or a supercomputer. In principle, you can run some simulations with your own laptop, but it will be like, I don't know, it's very short, maybe not a good resolution, and yeah, I don't know, it's better. I think it's better and faster when you have access to a computer cluster. So that's all for me. That's all from me. So okay, come back to the questions and open discussions. So just let me know if you have any questions.
Thank you very much, Dr. Yoshinta. Let's give her a big applause. So, any question from the participants? You can raise your hands, so you can talk directly. Okay, Subham. Yes, please, Subham.
Yeah, hi. Thanks for the wonderful talk. So I have a question regarding the electric charge of black hole. The first question you asked in the quiz, it was about the electric charge. Oh, sorry, my laptop's camera is not working right now, so it has some issues.
It's okay.
Oh, yeah. So I was asking about the electric charge. So far, like we have not observed any, like, are there any observations of spinning black holes?
Say again.
Because in the param
Uh-huh.
yeah, because in the parameters, you are choosing three intrinsic parameters: mass, spin, and the eccentricity, right? So
Yeah.
do we have any observational evidence of like the spinning of black hole? Like, have we ever observed the black hole with the spin?
Yes, we do have. We do have spinning of the black hole. Sorry if I understood your question. You asked about the spin, or you mentioned a bit about electric charge. You have any question about the electric
Yeah,
charge?
first spin and then electric
Okay,
charge, yeah.
okay. So I'll answer first. Yeah, we have observed some systems with spinning black hole. Although the spin, I think most of the systems that we observe have a relatively low spin. So here the spin is that I should say that here is the angular momentum divided by the mass. So this is between -1 to 1, or the magnitude is the spin magnitude is between 0 to 1. So the highest one is 1. Because and what we observe so far is there are some that's quite high, but it's not that it's very close to 1. But so most likely it's like low spinning system. But yes, we do observe a lot of spinning systems.
What about the charge? Do we have any observations of charge on black holes? Because in the intrinsic parameter it's not there, but
Yes.
in theories there is, like, we have charged black holes, right?
Exactly. Yes. This is a very good question. Yeah. Yes, in theory it is, and black hole have the electric charge, but for the gravitational wave observation, this is not in the electric charge is not in the parameter that we estimate, because electric charge is normally we see it in the electromagnetic observation, right? Which is gravitational wave is a different kind of wave here, and for the electric charge we don't see it. So we only have a mass, spin, and eccentricity, because it's not electromagnetic waves. Does it make sense? So in reality, in the black hole yes, it's true that the black hole has the electric charge, but in the gravitational wave, we don't have because we can't really see it.
Yeah. Okay. So in the modeling in future, in the gravitational wave modeling, so the community or the people trying to incorporate charges while modeling, or they are not like
Okay,
considering charging at all.
right. This is I think there are some works on that, on the electric charge. Um, it has something to do with the, if I'm not wrong, if with the black hole area theorem. I don't know if you have heard this theory by Stephen Hawking. So there are some studies about that, although I should say at the moment it's still quite very early. So we also try to understand that, and maybe if we maybe find the, I don't know, the relation between this and the electromagnetic observation from black hole. There are some studies about that, ongoing studies.
Thank you.
Okay, thank you, Subang. There's other question from Ashraf. Ashraf, do you want to say it by yourself, or I will read the question? I will read the question. It's on chat. So, what are the differences in the signal, especially at the ring down phase, for the black hole, neutron star, and neutron star? Since black hole has no solid surface, while neutron star has a solid surface.
Oh, okay.
Differences in the signal.
Are you okay? So I try to understand the question. The question is, what is the difference in the ring down phase of the signal between black hole, or binary neutron star? Yeah. I think okay, for this is interesting because for the black hole you will see this ring down. Let me see the odds. Let me go to the visualization of the signal for the ring down so I can show you. Is it there? No. Okay, goes back. Where is it? Okay, let's see here. Here, this is for example, this is black hole, yeah. If you see here, there is a peak, and then it starts to go a bit down, and then it's just flat after flat shortly, yeah. Because they became one black hole, yeah. They became one black hole. This is the ring down. But for the neutron star, it's true that they consist matter. So there are different fates of neutron star, and this for neutron star, for the shape of the black hole, for the shape of the black, you can see here, for neutron star, it will still be of ringing. So it's not just flat right away. I would say this is flat, yeah. But for neutron star, you still see some wiggling around, which we call the post-merger, because there neutron star and neutron star, when they collide, they can form either hypermassive neutron star, supermassive neutron star. They can also be a black hole. So this is interesting. You're right. This is the ring down. Is the interesting study of black hole and neutron star, and that's also the reason why I think why the Australian interferometers is about to build, because they want to study more about this area to know different fate of that. So I talk about the shape, yeah, but it's also different fate. Well, for black hole, it can be it will be a black hole, but for neutron star, maybe it will be different. Another thing is that this may be not related to your question, but the in spiral area here, so when they're still orbiting each other, and the length in spiral of black hole and neutron star are different. So when they close to each other, the neutron star, there is a tidal deformability. If you see it, I put it also in the quiz. Tidal deformability, it's a trick. It's a parameter of neutron star, not a black hole. So you can imagine like the Earth and the Moon. The Moon is tidally deformed. So it starts You can see it even more if it's a neutron star black hole binary. So it's a mix, one black hole and one neutron star. So the black hole sucks the neutron star slowly, and then the neutron star goes there. That you can see it from the characteristic of the wave here, the tidal deformability parameter. I hope it's clear, but let me know if you have follow-up questions.
Okay, thank you. Is it clear, Asra? There's another question from Aulia.
Okay.
Aulia, do you want to say it by yourself, or I will read the chat?
It's kind of noisy here, so can you please read it for me?
Okay, I will read for you. So I noticed that the discussion of gravitational waves on alternate theories of gravity mostly use post-Newtonian, as I have read through. But you say post-Newtonian breaks down when modeling gravitational wave merging down. How do you model the merging down signals on alternate theories of gravity? Could numerical relativity be used as well?
Okay, thanks. That's very good question. That's very good question. So currently I have a student working on that. So these alternative theories of gravity is basically it's not limited to post-Newtonian. Yeah, you can also use the semi-analytical model like in spiral merger ring down to do that. But anyway, there are some difficulties in the spiral merger link down. So the, let's say, Fano model or the reduced order model, there are some difficulties on that because they consist of like interpolation inside. Yeah. So if you want, let's say, to add some parameters there, and then the interpolation doesn't allow you to do that. Let's say the code doesn't allow you to do to add some parameters or to extrapolate it, then it doesn't work. So therefore, post-Newtonian is a good candidate for to learn about this. So that means we only take the binary when it's still spiraling each other, and we learn about the alternative theories of gravity by changing this post-Newtonian, because this is just like a long formula, right? Let me show you. This post-Newtonian is basically just a long formula. You can add maybe one term. Let's say in the alternative theories of gravity, the 6 post-Newtonian order has additional plus some parameters of exotic objects. So it's easy to put it in. So you can, to do the analysis, you can cut the waveform it's until up to in spiral until the post-Newtonian breaks down, and you analyze only that part. That's one of the idea. But in principle, if the model allows, you can also do that to another model, not only with the post-Newtonian. I hope that answered your question. Just let me know if you have any follow-up questions.
Okay, thank you. Subang, you raised your hand. Do you have additional question? Yes, please.
Okay, so from the waveform, how you conclude that, like if let's say we have a black hole merger. Okay, so after the ring down, it will settle either into a spinning or non-spinning. So how you conclude it from the waveform that it will settle into a spinning black hole or a non-spinning black hole, or is it always settle into a spinning black hole?
Okay. Okay, this is also an interesting questions you raised. Yeah. So what I said before, your first question about the spinning black hole, what I meant is the spin before the black hole collide. So I hope this is not misunderstood. So what I meant with the question before is before these two black hole collides, so the spin of each black hole. Yeah. And we have observed that. And now your question is, when they already merge, do these black hole spins? Yeah. So there are some studies about that. And if this actually, if there is a hierarchical scenario of where black holes comes from. So when the black hole comes from like from the globular cluster, and then they form a black hole, a single black hole, and then they meet to each other, and then they collide. Whether they come from there, or the black hole comes from the collision of two black holes. So it's like the first and the second generation. So let's say if you have two black holes, yeah, they form independently, and then they collide, and then there is another black hole, they also collide, and then each of them make a big black hole. Yeah, so now you have two big black holes coming from collision, and they collide again. So uh, uh, there are some studies about it, that that the final spin actually give hints on that. So the final spin is not always a zero. In fact, I think it's very rare that the final spin is zero. If they come from independent black holes, so like the first generation black hole and black hole collide, I think the final spin in the studies around, I don't know, 0.6 or 0.7, something like that. But if that comes from the second generation, it will have different. I think it's a bit lower. I'm not entirely sure, since it's been a while that I don't read this about the development of these studies. So no, it's not always. So you can see the spinning black hole at the end, and then it gives you hints of more physical evolution of the black holes.
Okay, thank you. So another follow-up. So when you talked about just now the neutron star merger, you said that uh, the neutron star merger could end up in any state like hypermassive neutron star or a black hole. So how you conclude from the waveform, like, because from the waveform we get some parameters, right? Intrinsic and extrinsic parameters we deduce from the wave, from the observations. So from that, can we like give some conclusion like it will end as a black hole or as a hypermassive neutron star? Is there any way?
Okay.
Or
Yeah. From the theoretical model itself, I think it's we are still working on the numerical simulations on that. But the problem is with the sensitivity of the detectors. So I would say for now it's quite hard, because the neutron star has a very low masses compared to black holes. Yeah, that means they have very long waveform. So if you compare what we see in the detectors, the black hole and black hole collision maybe is very short like this, while neutron star is like you see long in spiral. And our sensitivity, the detector sensitivity is not good enough for the post-merger area. So as I said before, that's maybe one of the motivations why we wanted to build the Australian detector, so that they can focus on the higher frequency to see the post-merger. But there are, yeah, you're right, there are different fates, and theoretically, I think we can distinguish these two between this, either it's hypermassive, supermassive, or they become a black hole. The problem is in the detector. At the moment, we also have a paper we just submitted about modeling binary neutron star, and focusing to have more in the post-merger area of the binary neutron star. It's a challenge also because that neutron star has a low amplitude compared to black hole collisions due to its masses. The accurate would be from numerical simulations. Okay, do you have any other follow-up questions?
yeah, okay, so you mean that there is theoretical explanation for the post merger of neutron star, but
Yes, yes.
observationally we don't. Okay,
Yeah.
okay, yeah, thank you very much.
Okay, thank you very much. Yeah, the topic is very interesting. But I'm sorry we have limited time. If you have more questions, perhaps you can also ask via email, Dr. Yoshinta? Is it okay, or via Slack?
Sure. I will also check my Slack from time to time, at least until the conference end. But if you have any questions, feel free to send me email. I will be happy to answer.
Yeah. And perhaps the participant can also try your GitHub. Very interesting. I've just opened it, right? For the simulation of gravitational wave. Okay. Okay, because we have only limited time, so we already in the end of the session. So please give a big applause to Dr. Yoshinta. And then please turn on your camera because we will have a position together. Dr. Yoshinta, is it okay if we turn off the share screen?
Yes, I do. I just clicked it. Okay.
Okay, please. Okay, wait. Okay, ready for first page. 1, 2, 3. Okay. Wait. Okay, next page. 1, 2, 3. Okay, last. 1, 2, 3. Okay, thank you all.
Okay, thank you. Thank you very much, Dr. Yoshinta.
Thanks.
Okay, participants, after this, you will have 15 minutes breaks. And then after that, you will have free session for discussion to prepare your presentation tomorrow. Okay, thank you very much. So see you again. Have a nice break.